Did we invent the numbers, like some made-up tool, or did we discover them? Maybe this seems like a frivolous question. Why care? Just get on with the calculations. But if some math is invented and some is discovered, then wouldn't paying some attention to this help us build our best tools, help our equations not blow up so much? For instance, in our persistent problems of the most foundational models of physics. Sometimes we forget, as useful as they are, that we've bottled uncountable infinities of both time and space in smooth and continuous space-time, all at once, everywhere in the universe. These important assumptions deserve some good questions. In this series of videos, we will look at math and physics with a healthy dose of artistic visualization, aiming to inspire without too much jargon, though some basics are assumed. You are encouraged to read further on any concept included without full explanation due to time constraints. For the most important concepts, you will see the formal math. Don't panic. You can let its beauty wash over you if you must, but I strongly encourage you to wrestle with it until it makes sense. The dividends are worth it. I am professionally trained. I have a doctorate in physics, but this is still a journey for me. There is so much that I am still learning and unlearning. In time, we will examine how relativistic constructions of numbers, including complex Quaternion, Octonion numbers and beyond, as well as games, may usefully bring new insights to old problems in physics, including how information is reconciled across matter and mind. We start in this initial episode with the surreal numbers and begin to unpack what they might teach us. To build from there, we'll work through a few flavors of explanatory context, so by the time you see the formal equations, you'll be ready for them. This is important for our applied thought experiments that follow. Before jumping into the surreals, let's take a hard look at their most basic ingredients, including the very concept of number, to help us break them down as monoliths. Let's think in symbols we're familiar with, without losing sight of what numerals point to. What is the humblest beginning of quantity? The concept of 1 is a good one. It's pretty foundational, but it cannot stand alone. 0 seems even more necessary, even if human cultures establish the concept as a whole after 1. But is there anything more necessary? How much further can we go? Too far. Don't worry, we'll return to you. Rather, we need to start as simply as possible. Here we go. This. Let's start here. It's not nothing, but it's close. It's our best representation of nothing. It's the empty set, the void. Empty of structure, empty of consistency, empty of coherence. So it's impossible to faithfully represent. It's not actually what you see. Here you see a pseudo-randomness, which is actually not very random at the end of the day. This is fake noise, which always has latent structure buried within it if you know how to look. Curly brackets with no symbol in between, a more familiar symbol for the empty set, or this, the null sign. Oh, it's just the same as 0? Not necessarily. 0 is our reference point of origin, used to measure the rest of the numbers, not exactly the shapeless, dimensionless, formless, unmeasurable, chaotic void. But modern set theory and its many mathematical applications cannot actually agree on this. My humble opinion is that they are not the same, and you'll begin to see why in a moment. Also note that to say the null set means something different in measure theory now, so we can no longer equate these terms. Measure theory's relevance to physics beyond its null set, which is more like a negligible set or subsets, will be future episode fodder. For now, we focus on the original wonder. But you might be asking, aren't we supposed to be talking about numbers? You wouldn't call the empty set a number? Well, I would agree with you there. We call it a set, but it could be an empty anything. Maybe it's not actually a set at all, depending on the context. Whatever it is that we're pointing to here, it might just be the most important generator of numbers, all numbers, and thus all form, all order, all pattern, and all structure in the universe. But we're getting way ahead of ourselves. The empty set has been an underrated friend of mathematicians for some time. Sprightly fellow and monster mathematician John Conway developed a special connection to the empty set, especially as he discovered one scheme to construct all numbers from the beginning out of nothing, or at least this best concept we have of it. Spending time with nothing, like John Conway did, begins to feel like everything. Conway was watching games of Go when he realized numbers were a special subset of all possible games. Namely, they are the totally ordered games, unfolding in order. Take a player on the left and one on the right, but instead of a game board, we have sets of numbers as our legal moves, or our freedoms. Each player has their perspective. New moves can be created in turn based on previous moves in previous games. They just have to follow one rule of order, which, as you'll see, looks familiar to any student of Dedekind or Euclid's fifth book, whoever the author. It may not be the most interesting game, or rather game of games, but in exchange for discipline and patience, we receive the numbers. All the numbers. All the integers, and with infinite patience, much more. It's not just a mathematical field. It's a proper class, which means it can do things that sets can't. It constructs not just the rationals, but the irrationals, and the transcendentals, and the ordinals, all of the reals and their extensions. This conception of numbers would later be called the Surreals by Don Knuth, Conway's collaborator on them. But Conway himself quite simply called them the numbers. He later explained the experience like he was walking around in a dream for weeks after his discovery. All it took was a rule of order and a kind of metagame, maybe the simplest. From all known moves for L and R, that's the left player and the right player's options respectively, you're allowed to create new moves that become new games in their own right by maintaining the rule of order. Conway informally talks about this rule as what defines the strength of a position in a game. Interesting. That means it's simultaneously relative while being a kind of mutual agreement. We can read strength more generally as a kind of orderliness. Formally, this breaks down into a generative rule and a discriminating check. For machine learning peeps, no, this architecture wasn't invented with GANs. Pitting a critical filter against a force of creation has always been how stuff gets done, at least stuff that survives the tests of time. I'll generally refer to this as survivors of exploration, a major reoccurring theme of this series. It manifests as evolution by natural selection, science and peer review, yes, learning algorithms, and even here at the base of math. Specifically to construct the Surreals. If L and R are any two sets of numbers and no member of L is greater than or equal to any member of R, then there is a number LR. You see Conway's convention here and what makes the defining cut. X is greater than or equal to Y if and only if no right set of X is less than or equal to Y, and X is less than or equal to no left set of Y. X is less than or equal to Y if and only if Y is greater than or equal to X, a bare and minimal agreement for an orderly game. X equals Y if and only if X is greater than or equal to Y and Y is greater than or equal to X. Pause to see it. Seems obvious, circular even, but that, my friend, is the iterative point on to find the numbers. The empty set features heavily, including from the very beginning when no moves are yet constructed. Here's a shorthand convention for what that looks like. Putting the void on both the left and right side gives us an equivalent starting position for each player, or what we'll call 0. And that's it for that game. Then games 1 and -1 are born, when each player takes that only existing move for themselves. Then 1/2, 2, -1/2, and -2. Then 3, 1/4, 3/4, and so on, as if the void is coming up with the most basic games to play with itself through the left and right personas by a brute force recursion. Before long, a veritable cathedral window of numbers unrolls before your very eyes, like an ancient papyrus. This exercise of relative relating, even if just one thing with itself, of iteration on the simple giving way to great depths, of seeking truth in the apophatic way, of duals and trialities and unity. Conway and his colleagues contributed substantially with formal riffs amongst ancient ideas to start simple and stay patient. So, to help on the journey, it's best to track when the numbers are constructed. Conway called these birthdays. Say you program a Turing machine to construct the Surreals. Not many lines of code, but it's going to take a lot of tape. It's going pretty well, so you step away to rest and come back to find such inconceivably large and small numbers. In a fit of mathy hubris, you decide to call these omega, as in the first ordinal, and its inverse. Yes, ... we have infinity. Well, it's only the smallest of infinities and largest of infinitesimals you defend your move, because you can't actually tell what the machine wrote. It ran out of room on the tape at some inconceivably huge birthday. So you write an omega over that buffer overflow. You laugh, saying you slept in past the first eternity. It's only like a joke because it's a math joke. And to get real, math may have gone to your head with your claiming an actual infinity. But really, this is all in your head, so it's okay. True Turing machines, with their infinite tape, can in fact only be imagined or suggested. This is some sort of mathy fever dream. As you look around your imagination at what has unfolded on day omega, you see more was born, the square root of 2, and all kinds of various numerical goodies. Pi, E, how surreal. But your original defense of modest infinities doesn't actually hold up over time, in more ways than one. As soon as you crank that machine back up again, you get smaller infinities and bigger infinitesimals, like omega over 2 and 2 over omega. Provably. And, well, it doesn't stop there. The Surreals can tickle your childhood ego beyond what even these imagined infinite friends do. Yes, I'm talking about your childhood ego who upped infinity with the infamous infinity plus 1. An infinity times infinity, an infinity to the infinity infinities. Oh, and their inverses. All by the archetypical proof by mathematical induction. Earlier it was finite, but from omega on, the transfinite method. And there are indeed brilliant and simple proofs for all you see here, many employing the careful tracking of birthdays of numbers. Yes, even if you had to dress it up in omegas and call it something fun like birthdays to be palatable to modern mathematics, Conway had, intentionally or not, brought something quite physical back to mathematics. It was time. As delightfully irreverent as Conway was on just about everything, he took the Surreals very seriously and considered them his greatest work. A deep respect for time, or we could call it dependency, is perhaps one of the greatest achievements at the core of the Surreals. At least we can read them this way, while still acknowledging what appears to be Conway's deep and fervent belief in infinity. He showed in elegant and concise proofs that infinity must unroll, but that it can also keep unrolling forever and ever, amen, and over again. Thus, omegas have an imagined form of existence, but there are quite literally strings attached. They start from 0 as a game of the empty set and rely from there on a consistent rule for games that looks an awful lot like causal dependency. A mathematics of dependency had actually begun to be formalized starting in 1935 with Whitney and Nakasawa. This is called Matroid theory, and very little work has been done connecting it to the Surreals, which were formalized about 40 years later. I suspect we have incredibly rich wells of potential to tap and further study of dependencies and their circuits. Not strange loops as much as normal loops, quite literally. Formally normed loops, Surreal Matroids hold intriguing potential to unpack the true reason to be thinking with infinities, or how we actually think at all. There is a critical ingredient we'll introduce next time before launching into what a surreal physics may look like. As I explore ideas in future papers and videos, I encourage you all to do so as well, whether the inspiration is to riff or to go running in the opposite direction. Along this highly imperfect journey, I would love to get your feedback in the comments below. In particular, I have to ask, Why do we use math like measure theory for causal set theory physics, rather than something like the Surreals? Eventually, we'll try to tackle this here. Our quasi-humble start in this video established what it looks like when the numbers are the manifestation of relationship. Of what with what? Well, none other than the empty set with itself, and all that ensues. In the next couple of videos, I promise we will work our way back to the empty set again, but in an ever more physical sense, rather than this beautiful, yet abstract representation of nothing at play before you. We'll continue exploring thoughts that, while fun, are deeply serious, like so much of what John Conway has helped us think more precisely about than ever. Maybe we're all what happened when the universe started playing numbers.